This is just going to be a quick video on for our science scholastical experiments you should know. These are not all the experiments you should know. These are just some of the more important ones. And as I make more and more videos, I will go through more experiments. So this is experiments part 1. So I think one of the most important experiments though is the Miller-Urey experiment. The basic idea is they were trying to simulate the early conditions of Earth and see if they could create amino acids or basic biological molecules. So what they did was they first they simulated lightning using this electrode with water vapor, methane gas, ammonia gas, and hydrogen. Water gas comes from this device here, which is simply a trap where you evaporate water, get the water vapor to come in, you start condensing some of it, you have a trap down here, and you take the samples, and then that's what you analyze for amino acids or different biological molecules. And you would input more gases time went on as it got used up for different reactions, and you'd keep sampling until you got what you wanted. That's kind of the basic idea here. So there is a volcanic version of this that actually produced more organic molecules, which is very interesting. So this does not simulate all of the. This is the most famous iteration, but there are different iterations of this experiment. And the volcanic version actually produced more organic molecules. But then the Murchison meteorite crash raised questions about the validity. Murchison meteor crash was a meteorite that crashed in, I believe, Australia, sometimes in the 2010s, so within this decade. And a meteorite crashed, and it had organic molecules on it. So then the question is, well, was it stimulated from something like the Miller-Urey experiment, or was it actually the Murchison meteorite? So this is basics of what you should know about Miller-Urey. I would know all of the chemicals and the basic formulation of this at the very least. And if you wanted to get the question earlier, the volcanic version and the different iterations and the Murchison meteorites are very good clues. Davison-Germer. Okay, so this one's a bit more complicated. Electrons were shot from an electron gun, and they were scattered on the surface of a nickel crystal. So we take electrons, fire them at this crystal, reflect them into this detector, and we see what pattern we get through Fourier transformations and different things like that. So then we display the diffraction pattern, and we look at it, what is happening. So it confirmed the idea of this wave-particle duality that exists. And it also confirmed the de Broglie hypothesis, which is the wave-particle duality. And it also assigned wavelength to massive particles, which was a very important key concept. It also measured the de Broglie wavelength, which is very important. And so this detector is actually a Faraday, what we call a Faraday cup, and it's just a way to measure electrons. So there's actually a lot of good clues in here. You may never see Davison-Germer as a toss-up answer, but it is a good clue for electrons, nickel, diffraction, de Broglie, wavelength, Faraday might come up. So, that's how you have to think about some of these things too, is, you have to know this information to answer other questions. So I can possibly see 1, 2, 3, 4, 5, 6 toss-ups just from knowing Davison-Germer. So you have the possibility, by just knowing these things, possibility of getting 6 toss-ups. So good one to know. Millikan oil drop experiment is very fundamental. This will come as a toss-up. It'll come up in bonuses. This will come up all the time. So Millikan oil drop experiment essentially measured elementary electric charge, or the charge of an electron. It was also awarded the Nobel Prize in Physics in 1923. So this experiment, what they did is they basically aerosolized oil droplets. They then charged these oil droplets with X-rays, and they dropped them between charged plates. And then what they did was they, using terminal velocity, they found where the oil droplets would stabilize between these two charged metal plates. So this, and then comparing the gravitational potential energy and the charge energy using Coulomb's law and different mathematical equations, they were able to find the electric charge. They were in equilibrium, right? Gravitational and an electrical force. So then they were able to find the electric charge by doing some mathematics and measuring the energy and the force. There was only an error of about 1% in this experiment, so it was a very accurate experiment. And that was basically due to the viscosity of air. And they used Stokes' law to calculate the drag of the oil droplets. So you lose some energy there. There were claims of fraudulence due to the low error and also unused data points. But as we know, this is fundamentally accepted. And those unused data points were mainly just due to flaws in the experiment. So very good experiment, very good stuff to know. Stokes' law is a good thing to know. Knowing why there was error is a good thing to know. So the toss-ups that might come from this are elementary electric charge, electron. This itself, it can be a toss-up. These charge metal plates, they might call them diodes instead, or they might see it as an early version of a capacitor. Highly doubt that. Equilibrium might come up because of Millikan. So, very good experiment to know overall. Young's double slit experiment. There's not much to say. You shoot a light between two slits, see what comes out. It's a diffraction pattern. As terms of what the experiment is, it's a very simplistic experiment in reality. But it demonstrates that light and matter can display characteristics of classically defined waves and particles. So this was de Broglie's pilot wave hypothesis. So this was like the first idea of wave-particle duality being a thing. It displays probabilistic nature of quantum mechanical phenomena. So for those of you who are unaware, or maybe just don't know what quantum physics is, so classical mechanics is very good for approximations and for very large objects. It starts to fail at the atomic and molecular level, as we will discuss a bit later, actually, with one of our experiments. And quantum is much more probabilistic. As you can see, we have constructive and destructive interference based on where these fringes are and where these very bright spots are. And there are some very dim spots. These very bright spots are where probabilistically the photons are going to end up. So that's what it means by the probabilistic nature. And it's less probable to come here. Generally in classical, we wouldn't have this probability. We would say, oh, this is the spectrum equally. Not the reality. So, the light diffracts through the slits, and the fringes are caused by interference. And specifically, destructive interference causes the dark spots, and constructive interference causes the bright spots. So basically what happens is when we have two waves collide, if one is at its peak and one of it at its trough, they destroy each other, kind of, in a process called annihilation. If we have two at their peak, they kind of add together and make a bigger peak. So it's kind of additive and subtractive in nature. Very simple way of describing it. But that's how it works. And that's why there's bright spots and less bright spots. And that has to do with the probabilistic nature that we won't get into too much more. There was actually a Mach-Zehnder variation, which used the mirror to split the beam. That's a pretty good clue for early Young's double split. So that would be like one of the first clues there. But other than that, I would know this experiment because it comes up all the time. In bonuses, it's a common toss-up. So good to know this experiment. Michelson-Morley experiment is one of the more interesting ones because it's actually considered a failure of an experiment. generally questions will phrase it as it disproved the existence of luminiferous ether or aether. But in the reality, they actually failed. They were trying to prove the existence, and they actually disproved its existence. So it's considered a failure of an experiment. So luminiferous aether, to understand what luminiferous aether is, basically it was the accepted medium that allowed light to travel. They didn't really understand how light traveled, so this was the common ideology, and the common acceptance of how light traveled was this luminiferous aether. But as the speed of light was constant in all directions, there was no luminiferous aether drift. And so the idea was speed of light would be faster in some directions than other, depending on how this medium was shifting, but it was consistent. More than that, it was consistent from a single light source. As we know, speed of light is constant. Really can't change it unless you pass through different mediums with diffraction and things like that. So they compared the speed of light in different perpendicular directions. So what they did was they fired a light source, and they had a beam splitter, which then split the beam, and then they fired it back through a mirror, and they were using interferometer to measure the speed of light here. And it was constant. They were trying to detect relative motion. Relative motion is this idea if I'm on a bus going 50 miles per hour and I throw a ball up in the air and I catch it, to me, in my reference frame, in my existence on that bus, the ball is stationary. But if we take a look from outside the bus, I'm an observer of the bus going this way, kind of. That ball is going up and forward. It's going, that's relative motion. So their thought was that light would be faster in some reference frames and slower in others because of how luminiferous aether would drift. They were wrong. So Michelson Morley also confirmed a postulate of special relativity, which was that the speed of light is constant in all reference frames. So this might be a toss-up for special relativity. And actually, Edward Morley, the namesake of the Morley aspect of this experiment, was so upset with this experiment. Him and Dayton Miller tried to find aether drift after the experiment, and they kept trying to find this. And you have to understand, you might think this is crazy, but you have to understand that this was kind of like saying to the scientific community that the color red is actually blue. That's how accepted luminiferous aether was at that time. So this was kind of saying, just throwing everything they've known out the window. So that's why they were kind of upset, and they were just kept trying to prove it, is because they would have to acknowledge that the knowledge they had was completely wrong, and that's not something they wanted to do. So Michelson Morley, luminiferous aether might come up, speed of light, obviously. Interferometer might come up in a bonus. Special relativity is very good to know. And this Dayton Miller clue, if you hear Dayton Miller, it's going to have something to do with Michelson Morley, probably. Dayton Miller hardly ever otherwise comes up. And this is a pretty good early clue. Yeah, and they were trying to find this aether drift I was talking about earlier. I think I said luminiferous aether drift, but this is what they were trying to find. Michelson Morley also comes up as a toss-up once in a while. Cathode ray tube experiment. Actually, not a lot to know here. This is what they created the plum pudding model based off of, and it's how they discovered the electron. Essentially, they fired a particle through this cathode, which is positive, went through a magnetic and electric field. It was expected to go this red way. Reality, it went this way. Figured out there was something negative in the electron, or negative electron. There was something negative in the atom. So they discovered the electron that way. Not too much to know here. honestly. Just know that this is kind of a late level thing for electrons, or maybe in a bonus plum pudding model, you might hear cathode anode, magnetic field, electric field, things like that in a bonus as well for this. Maybe phosphorescence will come up, but I doubt it. Rutherford gold foil experiment is actually much more interesting. It also is known as the Geiger-Marsden experiment. So actually sometimes they might just say it's called, also known as Geiger-Marsden experiment, this experiment. You know, it's the Rutherford gold foil experiment, period. Like, and that actually comes up sometimes really early on. So that just knowing that it's also the Geiger-Marsden experiment is very good. So this kind of disproved the plum pudding model. Well, it didn't kind of, it did. Because they discovered every atom has a nucleus where positive charge is centered. So what they did is they basically took a radioactive source to fire alpha particles at gold foil. So they're going to shoot something. What was expected is that it would go through, because that's how the plum pudding model would work. And if for those of you, actually I should explain the plum pudding model. The plum pudding model is essentially all electrons, protons, and neutrons are just in one big ball, almost like a plum pudding. And that made up the atom. That's not the truth. We now know that protons and neutrons make up the nucleus, and then there's an electron cloud. So what happened is when they shot these particles, they noticed that some would pass through, some would get reflected in different directions, and some would actually go straight back to the radioactive source. Why is that happening? Well, you have to remember, like charges repel like charges. So the alpha particles don't have any electrons. They're just the two protons, the two neutrons. It's the helium nucleus. Would be fired through this radioactive source, and it would go through towards this gold foil. Now, sometimes it would be able to slip through gaps in the atoms that exist and pass straight through and go undeflected. Other times, it would get closer to a nucleus and get deflected this way in different directions, kind of off-center, still within some probability, but then some went completely off course. And some even went straight back to the radioactive source. That was insane to them. Like, because again, you have to consider that this was like getting shot by your own gun, is kind of the a quote they kind of used to describe this. So this has to do with the repelling of like charges. So this screen is called a scintillator screen, is how they detected the particles, and how they counted the backward scattering, and it's made of zinc sulfide. So zinc might actually come up as a clue for scintillator screen. But that's the Rutherford gold foil experiment. And there were various variations of this to confirm the hypothesis. They did different ones in 1909, 1910, and 1913. They did one in a cone-like structure. It was a very weird one. But you don't really need to know that. But yeah, they shot a laser towards gold foil and expected it to just go through, because the plum pudding model, everything would be, there should be no repelling of charges, because all the charges are together. But they did repel. Why? Because we have a dense nucleus, which is very positive, and outwards we have the electron cloud, which is negative, and that's why particles repelled. Okay, Michelson-Stahl experiment. For this, you need to know what an alpha particle is, first of all. Alpha particle, again, 2 protons, 2 neutrons, helium nucleus. I would know that there were various variations. I would know the term scintillator screen, and I would know that it was made of zinc sulfide. Gold foil, knowing that this is actually gold foil, it will be very, very late level clue for gold as an answer. Geiger-Marsden experiment might come up as a bonus question, might show up early for a toss-up, things like that. Oh, they used a lead block, mainly because lead is, not very susceptible to radiation. The Michelson-Stahl experiment. This one's kind of easy. So, this was kind of proof of the semi-conservative nature of DNA replication, and that supported Watson and Crick's hypothesis. So what they did was they synthesized DNA that was all made with all nitrogen-15, which is a heavy isotope of nitrogen. And then they measured its density in, I believe it was DMSO they used. And then they did one replication of it, and it's only one band. And they were using nitrogen-14 after this. And they kept doing this replication and seeing what happened with the relative nitrogen-15 and what happened with the relative nitrogen-14. And so what happens is you see completely that the nitrogen-15 only continuously one strand just gets it, and it breaks down, down, down. And as we get through more generations, we have less and less and less ratio of nitrogen-15 to 14. And it's always consistently in one area. It's always at a consistent density. So this kind of showed that it was semi-conservative in nature, which means that one strand was completely kept intact and a new strand was synthesized with that strand. And they used E. coli as the model organism for this Escherichia coli. And cesium chloride, actually, it wasn't DMSO, it was cesium chloride was used here to separate the DNA. And if I may quickly, I will actually show you what the other ideas were for the replication, if I could find it. So this is the semi-conservative nature, which is one band stays intact. Then there was the conservative nature, whereas, the original band will stay intact completely. And we just consider a new strand completely. So this would have all been the nitrogen-15s, and this would have been all nitrogen-14. So you would have seen a very heavy one and a very light one. Not what we saw. We saw one get kind of lighter. This one is kind of wild. It's called dispersive, where random portions would be heavy, random portions would be light, and we would see DNA all over the place in that case. With the upper limits being only the nitrogen-14s, lower limits being the only nitrogen-15s. But what we saw was a very nice, even semi-conservative nature of DNA replication. And if you think of this energetically, it makes sense. This would take way too much energy to do. I would have to cut DNA here, synthesize a complete new strand, and then what am I copying? What is my template? It doesn't make sense. Conservative could kind of make sense, not the reality. Semi-conservative is the most energetically favorable, which is why life does it. Let's see. The Stern-Gerlach experiment. All you need to know about Stern-Gerlach is it demonstrated that spatial orientation of angular momentum is quantized. Complicated. It means that the answer will be spin. If you hear Stern-Gerlach, say spin. If it's asking for about spin. Otherwise, it'll be nickel, or silver rather. Maybe electrons, magnetic field, but most likely the answer will be spin if you hear Stern-Gerlach. So what they did was they kind of burned silver. They evaporated it and they fired it as a laser through a magnetic field, which was inhomogeneous. So it had different strengths all over the place. And under classical predictions, you would have an even spread of where the silver atoms end up. That's not the reality. because spin is quantized. It's discrete, which means it has set energy levels, and the probability of it being those energy levels is set. It's 50-50. It can be plus or 1/2, -1/2. And that's where they end up. They end up in two different locations based on what the spin was. Was it plus or minus? So that's kind of the essence of Stern-Gerlach, is how they measured spin. Then they did a lot of fancy math, which you don't have to know. Last experiments, there's no picture for this one because the pictures don't make sense for Ives Stilwell experiment. They were testing the contribution of time dilation to Doppler shift. Time dilation is the idea of things moving faster have a different time frame, or a different kind of, I don't even know how to explain this. They experience time differently. And so they were the first quantitative, Ives Stilwell was the first quantitative confirmation of time dilation factor in the world. The best example I can give is the International Space Station has time dilation relative to Earth. I believe it's like like a nanosecond difference of how the International Space Station and people aboard it experience time to the rest of the world. And this is not something like a lag or a latency thing. This is an actual difference in experience in time. This is kind of the idea, if when things travel at the speed of light, they fundamentally don't change. The faster you travel, the more you go on a change. It's because you experience time differently. That's kind of the idea of time dilation. So they used canal rays to measure the Doppler shift. That might show up. Other than that, it's one of the fundamental tests of special relativity. The other one we talked about, Michelson-Morley. And the other one is Kennedy-Thorndike, which I will talk about in a different video. But so you should know Ives Stilwell for special relativity, and Doppler shift, time dilation. Canal rays maybe show up, but other than that, you will be set. So that's the end of this presentation. This is the first video, so I'm going to hand this off to Mr. Brigham. Hopefully at least one of you watches it and will give me feedback of what I should do better. If you need more explanation on stuff, feel free to contact me. My email is chiragsha0121@gmail.com. I also will give Brigham the complete permission to give out my phone number to anybody who wants to reach out to me for anything. But thank you. I hope this was helpful, and please tell me if you would like more of these.